Welcome to Advanced Water Chemistry. And once we've done some water analysis of the water on site, we need to interpret that data. And interpreting a water analysis for our purposes in food service starts with a four-step process. And the first one is driven from input from our end-using customer. And principally, what is the intended purpose of the filtration solution you are going to offer them? Are we looking for product quality improvement, such as fountain beverage or coffee and tea taste and odor issues? Or are they looking for equipment protection, for excessive service bills or equipment breakdown, or to keep warranty specifications and their warranty good? Or are they looking for both of those benefits? And once we have that question answered, we can move on to step two with what are the applications? What are the pieces of equipment we're going to be delivering this water to, and what quality do we need to get it to? And we're going to collect whether that's ice, coffee, espresso, tea, or steam applications. We're going to gather the makes and models of those pieces of equipment. And then we're going to move on to step three. Once we've gathered that information, we're going to pull the spec sheets on those equipment and look for the water quality delivery standards to that piece of equipment or the warranty specifications for water in that device. And we're going to note that. And we're going to use that information to look at the raw water we have and look for where we need to get that water to. And moving on to step four, we'll be able to identify the appropriate water filtration solution technology and size it appropriately for our end user. Here's an example. The objective, or what our customer wants, is to meet the equipment OEM specs for warranty and get the water as close to the Specialty Coffee Association of America coffee specs as possible. So here's the lab analysis on the right, and it's raw information. Now we've gone on to that second step of identifying the applications. We have a 12-fountain dispenser. Those use 1.67 gallons per minute for the carbonator. That's the minimum flow we need. We have a 1,000-pound ice machine. It's a cuber, low flow, so we're going to be looking at up to 3 gallons per minute. So that's a total, let's round this up to 5 gallons per minute, and 2 pot brewers at a half gallon per minute each, so that's 1 gallon per minute for a total of 6 GPM. So we know how much water we need to deliver, how fast. Now let's look at the water quality. Well, we have the SCAA coffee spec to refer to. Well, here's what the SCAA spec is. Here's ideal. But most customers are going to be in the acceptable range for what we're shooting for. This is going to be much more for your high-end coffee shops or your small cafes that want to really, really deliver a high-quality cup of coffee as close to this standard as possible. And there's other resources in which you can get these specs from. In the front of the catalog, there is a page with the industry standards generalized for all manufacturers in the front. There's ice, coffee, and espresso, and steam applications in fountain beverage on that page. So it's an excellent resource. We go to great lengths to make sure we gather these specifications as close to what the industry is presently doing as we possibly can. So then we look at these numbers, and we're going to go back to that original analysis and look. Well, the TDS is a little low, alkalinity is a little low, and hardness is right in the proper range. pH is a little high, so we're really close to what this standard meets. With this water quality close to the SCAA specs, we're going to meet the OEM's warranty specifications, in this case for coffee. And since coffee is the most restrictive and demanding of all three of these applications, that's the one we're going to specify too. So we look at this water quality, and the only thing we might want to do for coffee is possibly add some mineral back to put it right into that acceptable range. Right now we're a little bit below. So in summary, basically what we need here is carbon-based filtration for either chlorine or chloramine to remove its taste and odor impact upon the beverage quality and any potential corrosion it could cause in the coffee brewers. Ice is all in spec. The only thing we really need to do there is chlorine or chlorine removal for taste and odor control, and use phosphate for long-term scale protection. And then coffee, it's in range, a little low. This is one place, if you have a very discerning customer, they may even want to add mineral content back here with something like a 7cc cartridge after chlorine and chloramine filtration to remove that taste and odor impact. But other than that, this is standard base carbon filtration. Now, temperature and water chemistry, there are some very profound effects linked to temperature. As we increase the temperature, we are going to drive the formation of scale based on the Langmuir saturation index. But another critically important one is corrosion, because once corrosion starts, there is no going back. And since most of our equipment in the food service realm are constructed of 304 and 316 stainless steels, we need to look at what causes that corrosion. And principally, the most aggressive thing in the water we have is chloride. And this chart shows a tolerance chart for chloride compared to temperature for these two steels, which are the most common in the food service. And what's important here is if you notice that all these different applications, their temperatures are close to boiling, except for ice, which is a special case. But as we get close to boiling, which is 100 degrees C or 212 degrees Fahrenheit, we notice that the tolerance for chloride for stainless steel to prevent corrosion drops to 0 somewhere around 85 degrees C or around 180 degrees Fahrenheit. So there's going to be corrosion if there's chloride in the water at boiling or near boiling. Most manufacturers of steam cooking equipment have their standard at 60 or below, most right around 30 parts per million of chloride. And the reason that is that level of chloride, the oven should make it through its warranty period without exhibiting any corrosion or any significant damage that would be unacceptable to a customer. So there's a cost-benefit selection done there. But as we increase temperature, we have to be aware of the impact of chloride on the stainless steel of our cooking equipment. And then there's the other indices that we use to determine what the water is going to do and what issues is it going to create. And I had mentioned LSI before. Well, LSI, it is the Langmuir Saturation Index, and it's an accurate gauge of whether the water will precipitate or cause scale to form, calcium carbonate specifically, or dissolve that calcium carbonate off the walls of the plumbing or boiling chamber. And it measures, and it's centered around 0, where 0 at a given temperature, which is important, 0 means it will neither form scale or dissolve scale. And when that number is negative, and the more negative it is, the more aggressively the water will dissolve calcium carbonate off plumbing or inside of components. But as that number increases and becomes more positive over 0, that's showing us that this water will cause scale at that temperature. And an interesting effect of temperature is as temperature increases, scale wishes to form. So we know if we have a 0 LSI at room temperature, as we heat that water, that number is going to become positive. And there's even examples of water that starts out as negative, slightly corrosive to calcium carbonate, but once it's heated, it becomes scale forming. So temperature is very important to the formation of scale. The other index we use is the Larsen-Skold index, and it's a measure of corrosivity in the water towards mild steels, 304 and 316 steel. And it is based on the ratio of chloride and sulfate, things that can create acids in the water essentially, to the amount of base or Tums in the water that neutralizes those acids. So when we have more of these aggressive corrosive salts in the water in a higher ratio to the base or Tums in the water, you get water that is corrosive at any temperature. And temperature will only increase this effect. And this scale is centered around 1, where less than 1, it is going to be scaling, and greater than 1, it will be corrosive. And this accurately indicates that this water will cause corrosion in on the steel. The higher that number is, the faster that corrosion will take place. Now, here's some major cities with their Langler Saturation Index and Larsen-Skold Index. And it's pretty interesting that in San Diego, your water starts out at room temperature, slightly corrosive to calcium carbonate. But as soon as we get near boiling, this water becomes scaling. And this Larsen Index is extremely positive, 2.12. And that will make this water corrosive. So what we're going to see here is potentially a buildup of scale and corrosion in coffee, espresso, and steam applications. And something very similar takes place in Los Angeles as well, based on these numbers. The larger the Larsen-Skold number is, more positive it is, the more corrosive that water is. Now, San Francisco is very, very interesting because it is aggressive to dissolving calcium carbonate at room temperature and at boiling. And it does have a slight little bit of propensity to cause corrosion, but very, very low. So we're basically not expecting to see any real corrosion damage or scaling in this water just through volume. Chicago city water is similar to that, but we start to form scale at boiling temperatures fairly easy from Lake Michigan water at this point in time, and it's only very, very slightly corrosive. Probably will not see any corrosion in an oven in this market either during the lifetime of this equipment. Now you have Dallas, which is slightly scaling at boiling temperature, slightly corrosive at room temperature, but very corrosive on the Larsen-Skold Index. And this is going to indicate that we have possibility of quick corrosion in cooking equipment here. So this lets us know the sorts of issues we're going to need to manage, and that lets us know which tools we need to select.